Hi, everyone. These are my slides. You can see the URL at the top, so if you want to look at them later, I hope you can read that. Right, yeah, so hi, my name is Alex Potsides. I am Aching Brain on the internet. I'm here to talk about building trust-free distributable applications with libp and IPFS. So a quick show of hands. I'm actually going to ask a question. Who knows about libp2p and or IPFS or has used it before? Okay, cool. It's about a third of the room, maybe? Anyway, that's good. Cool. So I work for Shipyard. We are a group of developers who build the tools I'm going to be talking about. I am the lead maintainer of Helia, which is an implementation of IPFS, all written in TypeScript. It's all ESM. We try to be web first as much as possible. I also maintain JS libp2p, which is one of 8, I think, implementations of the spec. There are implementations in other languages such as Rust, C++, Go, Java, that kind of thing. And who uses this kind of stuff? Well, so here's some of the logos of some of the companies. So these people all use the JS implementation. So Farcaster is a social network. Recently had like $1 billion valuation. Strata is new. They're going to be trying to solve some retrieval problems for distributed storage. Wacom do great stuff on mobile. Lodestar is it's an Ethereum consensus client. Runs on TypeScript. It processes about 3%, I think, of all the transactions on the Ethereum network, which might turn some people off, but this is like billions and billions of dollars, like stupid amounts of money of transactions throughout the year. So if you're interested in running like JavaScript at scale with like really high consequences of getting it wrong in very adversarial environments, I mean, this is it. Orbit is a database, and then there are lots of others. So let's get into it. So what is libp2p? Originally, it was the networking layer of IPFS, and it was extracted because people decided it would be useful. It's a modular networking stack, which is basically just to say it's a toolkit designed to solve common problems when designing distributed applications. So at the heart of it, libp2p is the ability to make connections between two computers or nodes over which we can send some data. The transport is abstracted away, so it can be WebSockets, WebRTC, TCP, depending on what's available on your platform. And libp2p provides a transport-agnostic abstraction that you can interact with. We encrypt everything that goes through this tunnel. Some of the transport support encryption natively, such as WebSockets, such as WebTransport or Quick. If they don't, then we add encryption on top using either like TLS or the NICE framework. And then we add multiplexing on top of that. So the idea being that connections are expensive to make, and then streams are very cheap. So you make one connection, and then you can open multiple virtual connections, which we call streams, over that connection. And again, some of the transports provide this natively, like WebRTC, and others don't, like WebSockets. So we have to add our own muxing on top of that. So you can take a look at the types of transports that are available. So this is from the connectivity, the libp2p connectivity website. So you can see in JavaScript land, we have pretty good browser connectivity. I don't know why Quick is blue there. It's definitely not in browsers. But the one thing that's really missing from Node is Quick. And we really Quick is super important because one of the biggest challenges with designing with using distributed applications is connectivity. And if you can't connect to another node, you're kind of dead in the water. And that means punching through NAT firewalls or doing NAT traversal. And for that, TCP is useless because it has retries and backoff windows and that kind of thing. So when you're trying to punch through a NAT firewall, you have to have very reliable timing. And TCP does not give you reliable timing. So the success rate of that is really poor with TCP. With UDP, on the other hand, you do get these kind of guarantees. And what Quick does is it adds in more retries than bare UDP, but not as much as TCP. So you have more reliable timing. So it's much better at hole punching than TCP is. But it's not in Node yet. There is WebTransport as well. WebTransport is built on top of Quick, so it gives you those nice UDP properties. It doesn't exist in Node yet. I do have a PR that's been open since February to add web transport support to JS libp2p, and it's via this fails components module, which exports libcache bindings, which then lets you do web transport, and ultimately it will let you do Quick as well. But it still needs quite a lot of work. Because every time I use it, there's some weirdness in how it interacts with other implementations of the spec, which never seem to quite work properly, which you'll see might become a bit of a theme of this talk. Another attempt is this, which is currently ongoing via ChainSafe, who's one of the collaborators on JS libp2p. So this is trying to take the Rust crate for Quick, compile it to WASM, and then use it in Node, which is gross. I don't know if anybody actually enjoys working with WASM. I certainly do not. It's just a big blob of code, or a big blob of binary that you can't really see into, and obviously you need to copy memory in and out of it, and it's quite slow. But slow is better than nothing. So that's here if you want to check it out. I particularly like the last, I took the screenshot this morning, I particularly like the last commit on there, fix CI. I think if you have a commit like that, you immediately doom it. It's gonna fail. Like fix tests, fix CI, it's gonna fail. And as you can see, the nice red X next to it means that it failed CI. Now this is super exciting. This is the PR to add the scaffolding for web transport and Quick. Well, to web transport built on Quick to Node, and this is by James, who sat in the front row here. This is amazing. Absolutely incredible to actually have been flying, holding the torch for Quick for so long. I'm super excited about this. I check this PR every now and again to see if there's been any progress on it. And yeah, so it's soon. TM, you heard it here first. Yeah, I'd love to help land this in any way that I can, because this is going to open up so many new avenues for distributed applications based on Node.js. What else does it give you? So libp2p has loads of protocols that are like application protocols that are built on top of the transport. So once you've got your network connection, what do you do next? So they're all they're based on academic papers, a lot of them. So we have Academia-based DHT, which gives you peer lookup discovery along with record publishing and resolution. There's BitSwap for file exchange. This is used by IPFS quite a lot, and we'll see a bit more about this shortly. GossipSub is a PubSub implementation for distributed systems. It's got quite a heavy focus on security and hardening, and it's what the Ethereum 2 consensus layer is based on. That's the new one, the proof of stake one, the one that isn't killing the planet. We've got things like AutoNat, so you can discover your public addresses, which is a bit like Stun, but without having Stun servers. Instead we take requests from lots of different peers on the network. Circuit relay, which allows us to, this is like a public good relaying system, which allows you to let other peers relay small amounts of data for a limited amount of time. And it's what makes like dialing WebRTC possible, for example, without going via a centralized SDP server. And lots more. There's a specs repo. It's full of stuff. Some of it even works. Some of it is half-baked. So if you spot anything that's half-baked, I mean, you can open a PR to the spec, or if there's something missing, or you think something can be improved, please do get involved with the whole specs process. And if you want to try out writing protocols, we have the protocol adventure, which is like the old school, node school, like CLI self-guided learning tools, where you will start from sending raw data between two nodes going all the way through to distributed RPC. Is it fast? Like a lot of this stuff, distributed systems are not fast, which is very true. So, the things that we can control being fast, we definitely try to make fast. So this is more like, is it fast compared to other implementations? So this is JS fast? So JS is slow, right? It's a toy language. Well, I mean, so here's the results of some benchmarking that I did. This is standing up two servers on opposite coasts of the US, transferring a bunch of like gigabytes and gigabytes of data between them, and then timing it and working out what the throughput is. And you can see that the JS, like, so on the left, the HTTPS is as fast as HTTP can go, so it can get up to 5 gigabits a second. And then you've got different versions of Go. Quick Go is just quick, so there's no libp2p involved. And then there's JS at TCP land, and it is actually the fastest libp2p implementation for streaming, which is not bad for a toy language. This is due to a lot of optimizations of trying to remove unnecessary async work and ensuring that we don't actually copy any data ever. When your protocol emits some data, it's that buffer that goes onto the wire as far as possible. So when we do the encryption, we have to copy, like the encryption algorithm will copy the data at that point. But otherwise, apart from that, the libp2p layer itself doesn't actually ever copy your data. So it's incredibly performant. That's libp2p. So a quick primer on IPFS. So what is it? So IPFS is, the basic idea of it, you put a file in, you get a CID out, and then later on you can put a CID in and get a file out. I'll come back to CID shortly, but they're like a hash, but they're not a hash. It's not true to say that like I'm just going to SHA-256 my file, and that will be the CID. Unfortunately, it's not true. Behind the scenes, your file gets broken down into lots of chunks. We call them blocks. And each block is assembled into a DAG. Every block has a CID, and then the DAG itself has a CID, because the nodes that aggregate the blocks are also nodes with CIDs, etc. So this is what a CID looks like in its totality. Isn't it beautiful? Very easy to understand. But what do we use it for? So the novel thing about this is that we use it for addressing. So if you imagine, if you're making a request from a web server, you have a URL and a path, which is used for addressing, whereas here we actually use the CID for addressing. But like, what's wrong with URLs? Like, nothing is wrong with URLs fundamentally, but they do have a lot of trust baked into them. So starting off, like, we're using SSL, which is great. No one can eavesdrop on the transport. But how do we get that certificate? Like, who issued it? Like, is the certificate still valid? And why do I trust it? Is it down to the CA certificates on my computer? Like, who installed those CA certificates? Are they the ones I expect to be there? If you think about corporate environments where you might get a corporate image on your laptop, it's probably got some custom CA certs on it, so that when you're connecting to the internet, maybe they're gonna generate a certificate for Amazon.com when you access it, and you would never know unless you checked it yourself, because the CA cert on your server says, hey, this is all good, because the dynamic certificate was trusted by the CA cert. What else? So DNS, I mean, we're all aware there are DNS poisoning attacks. You could end up going to the wrong server if if it resolves to a different IP address. And is it blocked? That kind of thing. And then the actual path itself. So obviously you're then at the whims of the web developer, like, does the path still exist? Has the content changed? Did I actually get what I wanted? Has someone like swapped it with a picture of something that I didn't want to see? Is to say, like, URLs are not bad. We use them a lot at Shipyard. The nice thing about the CIDs is that because it's a hash, as long as I can recreate the DAG of the file, and then I can validate the content that I get back by the CID. So we use this in the HTTP gateways that we run, which bridge HTTP and IPFS. So you can make a request or a URL with a CID, and you get some content back. And we publish a couple of modules, Verify Fetch and Helio HTTP, which will do the verification for you after you've downloaded the file. So you can have it all be trustless, which is quite nice. So that's what CIDs are for, but we're like, what are they inside? So if we go super deep into the weeds now, so this is a CID, this is a website, cid.ipfs.tech. You can stick a CID in there, and it breaks it down, and it shows you what the CID is made up of. So the first thing is, there's a multi-base, what, base 32? What is that? So what is it? What is it? What is this? Like, this is what multi-base is for. So what is this? It's a string, right? It's probably hex encoded, maybe? Like, it looks kind of familiar. Yeah, it is. Let's say, yeah, it's base 16, hex encoded. Easy. What about this one? So this is base 64. Cool. Is it URL safe? Who knows? What about this one? This one is base 58 BTC, which is, for some reason, much beloved by Bitcoin people. This one is base 36. No, I'm just kidding. This is base 32. Right? I mean, you never know. But like base 32 has a nice property that it's case insensitive, so you can use it in URLs, which we might come back to later. Multi-base is just a convention. It just says stick a letter on the front, and the letter tells you what the encoding of the rest of the string is. So suddenly you can decode it, you can accept any string, and you can decode it and get the right data. This might seem a little trite like this, but if your data looks like this, if you decoded each one of these, they actually have different values. So it's really useful when your data is ambiguous. These prefixes are all standardized. There's a CSV file which has them all in. So if you invent a new one, you can get it added there. So we know what multi-base is now. We have a version number, pretty simple. We have a multi-codec, and the codec just tells us how to interpret the data in the block behind the CID. And a multi-hash. So finally we get into the hashing part. And it's a multi-hash like a multi-codec, like a multi-base. So you may have guessed that there's going to be a prefix in there that's going to tell me what the kind of hash is. So we've got some examples of the hashes here, so you can combine them with multi-base. So at the top we have base 32 and SHA-256, and then base 16, SHA-512, and then base 256 emoji. Why not? And SHA-1, because jokes. The codecs for the numeric values for the hashes and the codecs all live in this table in the multi-codec org. That's it. That's the ID. So like, what's next? So IPFS, you stick files in, get a CID out, get a CID, stick it in, get a file out. It's not free storage. It's a distributed system, but it's not free storage. This is like one of the misconceptions I think about IPFS a lot. We hear people talk about uploading my data to IPFS. It's not true. The data stays on your local node at all times. So we're not really storing data on IPFS. We are making data available on IPFS. So I have a file. I turn it into a CID, and I do a Kademlia query. Now, Kademlia queries are all based on XOR comparisons, which you may remember from university or one of the talks earlier. You basically have two buffers of the same length. You look at each bit in the buffer, and you do an XOR. And if they're different, you have a 0. And if they're the same, you have 1. And then we can derive a number from that. And then the lower that number, we consider it to be closer, like CAD closer is kind of the terminology that we use. So how does it work? So I take my CID, I take the multi-hash out of it, I hash the multi-hash. Why do I hash the multi-hash? I'm glad you asked. It's because hashes can be different lengths, and if we're going to do an XOR operation, we need both buffers to be the same length. So I've now got my CAD value that I want to find on the network. So I have my CAD value, I have some nodes on the network, and I ask every node on the network, well, first of all, every node on the network has its own peer identifier, and I can derive the CAD value of each identifier. And so I ask every peer on the network, who do you know who is CAD closer to the value that I'm trying to look up than you are? And they'll say, oh, well, I know these peers. And then we repeat the operation, and we say, who do you know who's CAD closer to this value than you are? And we repeat this until eventually we arrive at a set of peers. The number is defined by the paper, which is 20. And once we've found the closest set of peers, we send them a provider record. And the provider record just points back to me and says, this is where I am on the network. If anyone asks and they want the data, I'm over here. So to then look it up, we do the same operation the other way. So we start with the CID, we ask the peers, who do you know, who do you know? And then eventually you find the peer, you ask them for the provider record, and then you can contact the original peer who published the provider record and say, please give me the data, and they give you the data. So the nice thing about all this is because we don't need to trust any peer at any point, because when we receive the data, we can verify that what we receive is what we requested. And there are certain in-protocol mitigations for things like, because you could end up contacting a bunch of peers and they send you some bad data, but there are in-protocol mitigations to make sure that we run queries with lots of peer diversity. So that's to say, we will contact peers from a range of net blocks, because they will typically be in different data centers, and it's expensive to stand up lots of peers and lots of data centers, and a lot of the mitigations of network attack patterns, a lot of them, if they're not in protocol, then they focus around making it expensive to actually perform the attacks. So we can look at some of the attack patterns quickly. Some of them are old, some of them are new, so you'll probably recognize quite a lot of them. Disclaimer, this is an evolving space. There's lots of interesting research being done, and I'm not a security researcher, so I apologize if I get any of this stuff wrong. But like, man in the middle, like this is a classic. Everyone will have heard of this one. HTTP is pretty vulnerable to this, and SSL doesn't help that much when you consider you could have bad CA certs on your machine, as I talked about earlier. The classic denial of service, you've got lots of bad nodes attacking one, and it makes it hard for legitimate traffic to get through. And then like resource exhaustion. So if I have like a peer ID that's cheap to generate, for example, and I just reconnect to the same peer multiple times, and then if that peer is storing information about the peers it knows about, eventually it might run out of storage and fall over. This is a real problem sometimes. Not with JS though. JS doesn't have this problem. But yes. So a Sybil attack, this is a more distributed systems specific one. In a Sybil attack, you have one peer on the network that has multiple identifiers, and so it can influence more peers cheaply because it doesn't have to maintain separate connections and separate data centers and that kind of thing. An Eclipse attack, this is when you behave like a good citizen until you're not a good citizen, and then suddenly you can isolate peers on the network, and you can send them data that will cause them to question their viewpoint of the world and perhaps behave in bad ways. One example of this is a theoretical attack where you have a healthy-looking network, and then the target peer goes offline, and then some peers turn out to be malicious, and then they're evicted from the network because we've detected they're malicious, like how? Through in-protocol mitigation. So Gossip Sub, I talked about earlier, has this very easy to understand formula that scores peers based on their performance and their behavior, sorry. So if they're slow to connect to you, or if they send you lots of duplicate data, or they're sending you rubbish and that kind of thing, it all feeds into this. You should take a look at the paper. It goes through lots of attacks and mitigations that are baked into the protocol. Anyway, so the peer's been knocked offline, our network has become disjoint, so we now have two separate networks. The target peer comes back online, but it doesn't know that the other peers are bad. Now we have two separate networks that are performing the same amount of work. So this is a theoretical attack which you can use to perform a long-range attack, which is if you have these two separate networks and you start from the genesis block of a chain with something like proof of stake, where you don't need to consume lots of computing resources to get the longest chain, you can now just create two chains in turbo, or one chain in turbo mode that becomes longer than the other, and then people who connect to these networks equally, because they're using the same protocols, will typically pick the longest chain. And so at that point, the bad disjoint, half of the disjoint network, becomes the one that has the authority to write the next block. Don't think it's actually been exploited yet, but it is a thing that's in the literature. Speaking of literature, there's loads of it. Like, there are lots of really interesting papers out there, which you can read and discover more about this stuff and the different mitigations against it. There are a few little things that we can do to make the applications that we design better and more stable. So finding peers is really hard. It's also really hard when you're trying to be in browsers and other platforms that maybe don't support all the transports. Like the thing I hope you take away from the explanation of how you publish a provider record and then resolve content, it relies on the publisher and the resolver both resolving at least some of the same set of peers that host that provider record. Like if you can't do that, you're stuffed. So it relies on both of those peers having the same view of the network. So if they can't talk to the same peers to trace the same journey through the network to arrive at the host of the provider records, you can't, like, you won't be able to resolve anything. And this is a problem that the IPFS has in the browser lots, because most of the nodes, most of the provider records are stored in Go nodes, which run quick in TCP, and they're not running WebSockets or WebRTC or anything that they can talk. This is going to change in the future. We're going to ship SSL like let's encrypt style certificates for everyone so they can run WebSockets and then browser will be able to connect to them. It's coming soon. It's going to be very exciting. But the easiest way to do it is just to stand up your own bootstrappers. So if you have your own custom protocol that your application is running, you just stand up a bootstrapper and get everyone to connect to it, run a DHT using that protocol, and then suddenly everyone who speaks your DHT protocol knows that you can speak to. So the bootstrapper just knows who else is online, and you say to the bootstrapper, who's online? And then you can connect to these other peers, and you can join the network. Or like maybe you'd use a different approach, a different custom protocol. Again, if you look at all the research that's been done into peer-to-peer systems, there are loads of different protocols that you could implement, and then maybe share them, and then maybe other people start using them as well. The other problem with browsers, obviously, is they go away. So you navigate away from the page, or you close the window, or shut your laptop. Like, how do you make sure the data is still available? Obviously, that's very hard because the provider record thing pointing back to you. So how do you get it? Oh, no, I've gone away. So you can either stand up a node yourself that is longer lived, that's more like an application server, and tell it to please store this content on your behalf, slightly centralized, but we've got to be pragmatists at some point. Or you can use hosting services that will serve it for you. So these are companies that will make your data available cheaply on the distributed web. There's a whole bunch of them. And some of them will take your data and make it archivable for the long term with like Filecoin deals and that kind of stuff. But yeah, it's fun. So there's less of a problem if you're just consuming content, because a lot of the content is available via gateways. But yeah, if you want to store content, if you want to be a content author, then you have to think about how the data persists beyond the lifetime of your node if your node is short-lived. Anyway, I've run over slightly, but that's it. That's the end of my talk. I'm Making Brain. Here is me on GitHub. There's the links to the projects that I talked about and Shipyard. So thank you very much.